Hi, my name is Marielle von Stein, and I'm presenting on automated generation of transformations to mitigate sensor changes in ADS. So here we see an autonomous driving system with an onboard deep neural network, or DNN, navigating a driving environment. In the upper left-hand corner, we can see the image that is being fed to that DNN, which the ADS is then using to steer around the topology of this road. Now, with a fisheye lens camera and the same DNN, we see that it swerves across the road surface until it crashes to the side. Critically, these sensor changes are common, and their impact to the system is significant. Here are a set of example transformations: depth of field, fisheye, and resolution decrease. Highlighted in the table, we can see the real-world systems that these changes have occurred in, the camera hardware migration that brought them about, and the image change that results. Across the bottom, we can see that the steering angle from a DAVE2 neural network is significantly affected by these camera changes. With that in mind, we present Prefixer, the first technique to mitigate such sensor changes in ADS with a high rate of success, low cost to implement, low demands on the developer in terms of time or domain knowledge, and minimal disruption to the ADS pipeline. The standard perception sensor to DNN to driving signal pipeline breaks down in the presence of new sensor hardware. So, Prefixer uses a VQVAE to map from the features present in readings from the new sensor hardware to the old. Because Prefixer is trained to reconstruct images in a way that preserves the prediction from the driving DNN, these reconstructed images are able to drive the vehicle using the DNN trained with data from the original sensor C. Prefixer is comprised of 4 main steps. First, we collect a dataset for collocated sensor components with the old sensor and the new sensor on board the vehicle. Then, we configure the augmented encoder in terms of encoder architecture, hidden dimensions, embedding dimensions, and number of embeddings. This encoder is then trained on the collocated dataset that we collected in step 1. Loss for this training involves the original DNN that is used to navigate the ADS, as well as reconstruction loss and embedding loss. In the last step, we deploy the trained encoder as a pre-processing module for the original neural network, which allows us to use this original network with the new sensor. Here we can see the ADS driving with the Prefixer pre-processing module on board. The fisheye lens image is input to the Prefixer module, which then outputs a reconstruction, which is then passed to the original DNN for driving, which is able to then navigate this road successfully to the end. Our study explores 2 research questions. 1. How effective is Prefixer compared to other techniques in supporting common camera sensor hardware migrations? And 2. How much data does Prefixer need to successfully learn each image transformation? Our study setup explores the system under test with the new sensor on board on 10 tracks of 100 meters each. The sensor undergoes 4 hardware migrations: depth of field, fisheye, resolution decrease, and resolution increase. We compare against 3 baselines: bespoke transformation only, transform and retrain, and fine-tune. BTO involves a transformation as a post-processing step on the original DNN. Transform and retrain transforms the entire original dataset and retrains the network. And fine-tuning fine-tunes the weights of the original DNN using smaller datasets from the new sensor. Prefixer 50K has the highest average performance compared to all other techniques using a 50K dataset and with BTO, which uses a transformation as a post-processing step on the original DNN. BTO has the lowest spread and second highest average across transformations, followed by fine-tuning 50K, then transform and retrain 50K. Moreover, Prefixer performance has significantly lower susceptibility to dataset size than fine-tuning. For a common set of camera sensor hardware migrations, Prefixer can learn an effective transformation with 1/3 or less data than it takes to retrain a full network. Even when compared with the best performing baseline, bespoke transformation only, or BTO, Prefixer can match or improve the performance in terms of distance traveled safely with 10% of the training dataset and take at most half of the training time of a new DNN. Prefixer is the first unsupervised low data transformation technique applicable to a wide range of common image transformations to mitigate sensor hardware migrations. We show that Prefixer can successfully learn transformations with high prediction accuracy even from small datasets by leveraging the knowledge of the previously trained base network. Please refer to the GitHub artifact for further details.